So to summarize, when I'm looking at two different compounds, and my question is, which is more acidic? Or even if I'm looking at two different protons within the same compound, which is more acidic? My question then that leads to is, which of the conjugate bases is more stable? Okay, so a question about acidity is really a question of stability of conjugate bases. Once I find out which of those conjugate bases is weaker or more stable, then that will point to the more acidic conjugate acid. So that's how I determine which is more acidic. How do I answer which is more basic? Well, it's not the opposite, right? So you might be tempted to think, oh, well, strong acids are weak bases and strong bases are weak acids. And so if something is a really, really bad acid, it's a really good base. That's not how it works. There's lots of things that are really, really bad acids and really, really bad bases, right? Like most carbon molecules, most CHs are really, really weak acids and really, really weak bases. And so this is a separate question. So, but we're going to follow a similar thought process, and actually an easier thought process. So if I want to know which is more basic, I'm asking which of the bases is more stable. Now, that can be compared with our second step up here. But notice the difference. Up here, I had to look at the conjugate base. And this, when I'm looking at basicity, I don't even have to do that. I don't have to think about what the conjugate base is. I just look at the base itself. So that's cool. All right. So, and again, how am I going to look at whether the base is more stable? Exactly the same way I'm looking at conjugate bases. I'm thinking, is the charge on a nice electronegative atom? Is the charge spread out over a big atom or over a group of atoms? And once I figure out which of the bases is more stable, well, that one's a weaker base, right? Because again, when we say stability, we mean lower in potential energy and lower in reactivity. And so that one will be less basic. Let's take some small examples. Which is more basic? CH3OH, CH3NH. Okay, so again, when I'm thinking about what's more basic, I'm thinking about lone pairs in particular. Right? Carbon's got 4 bonds already. Carbon isn't going to be taking a 5th bond. That's just math. So here, my question is, which of these lone pairs is more stable? And because I'm comparing stuff across a row, I can really think about electronegativity. Oxygen is more electronegative than nitrogen. That means that it's able to hold those lone pair closest to itself, which means that more electronegative, this is more stable, which means it's a weaker base. So this is a stronger base. Also, I can look at things down a row. So nitrogen and phosphorus. Phosphorus is below nitrogen in the periodic table. And so these electrons are more spread out. They're able to take up more room. They're able to minimize electron-electron repulsion. And so that lone pair is going to be stabilized by that reduction in repulsion. And so that means that this NH3 is going to be more basic than pH3. So here's a question. Which of these is more basic? Piperidine or morpholine? Two very, very common pieces of drugs. So I guess the first question we should answer is, if we look at this one, what's more basic, the nitrogen or the oxygen? So remember, when we're comparing along a row, we think about electronegativity. Oxygen is more electronegative than nitrogen. Oxygen does not want to use those electrons to go make a bond. Oxygen wants to hold those electrons tight to itself. Nitrogen doesn't really want to hold those electrons tight to itself. It wants to make a bond. It's going around saying, hey, do you want to make a bond? Let's make a bond. Okay? So here, morpholine, yes, the nitrogen is more basic than the oxygen, quite a bit more basic. Now, comparing morpholine to piperidine, does this oxygen affect the basicity of the system? When we think about stabilizing the electrons, right, we're talking about basicity. So we're talking about okay, which of these lone pairs is happier, more stable, lower in potential energy. And we can think of this oxygen as having an inductive effect, right? These carbon-oxygen bonds are a little polar. They're pulling, oxygen is pulling electrons toward itself, and it can kind of pull down the chain, so to speak, so that these lone pair electrons feel a little pull away from nitrogen toward oxygen. And being able to spread out those electrons is stabilizing. And so we would expect that this is a weaker base than this, because these electrons can spread out a little bit toward oxygen, where these electrons cannot spread out. They can't really do anything but go be a base. And that's exactly what we see. If we look at the pKa-H, so the pKa of the conjugate acids of these things, the conjugate acid of this has an acidity of 10.9 versus 8.4. So the conjugate acid of this is a weaker conjugate acid. So weaker conjugate acid means stronger base, because oxygen is having an inductive effect on this nitrogen. Which of these two is more basic? Here I'm looking at the same atom. I'm looking at the basicity of nitrogen in both of these cases. But there's a difference. Here I've got a resonance structure that I can draw. Go ahead and draw that resonance structure now. Notice that I didn't actually take a proton away. All right? I don't want to give the impression that we only see resonance with conjugate bases. And so what does this resonance structure tell me? This resonance structure tells me that this lone pair spends some time up around this oxygen. And so this nitrogen is a little bit more positive than I would expect, and the oxygen is a little more negative than I would expect. In terms of basicity, what does this mean? Well, here we are stabilizing these electrons by letting them delocalize. This structure is stabilized by resonance, and stabilized means it's a weaker base. Again, stabilizing meaning I'm taking the potential energy and bringing it down so it doesn't really want to react as much. So here's the experimental data. To remind you, this is the pKa-H. So this is the pK of the conjugate acids of these things. A high pKa-H means a relatively weak conjugate acid. A relatively weak conjugate acid means a strong base. So this is a relatively weak acid, and so that's a pretty strong base. This is the conjugate acid of this is very, very strong, stronger than HCl. And so that means that this is a very weak base. It's a weak base because it's stabilized. The electrons are stabilized by resonance.